Thank you very much. Again, as like all the speakers, I would like to thank the organizers for this nice conference in this nice location. This is all the work that's 8 or 9 years old. So there is, this is joint work with Jun-Yan from the University of Connecticut. The talk will be, I will make it short because we are all tired. And also it is relatively light in terms of mathematics. The idea is to draw your attention to some unsurprising consequences, basically, of the central limit theorem in some sense, and to show that you can use these consequences to get a faster version of the parametric bootstrap in goodness of fit testing when your sample size is large. So the outline of the talk is the following. As a setting to present the main ideas, I will consider that of goodness of fit testing when parameters are estimated and when we are using the empirical distribution function. In the second part, I will present this alternative to the parametric bootstrap, and I will briefly discuss some practical aspects and variations of this idea. So the context that I will choose to just illustrate the ideas is the standard one. We have a family M of parametric absolutely continuous distribution functions on R to the D. The parameter space is big O. The parameter is theta. We have at our disposal a random sample with a common unknown CDF F, capital F, and we wish to distinguish between two hypotheses: the null, that F belongs to this model, to this family M, against the alternative that F does not belong to M. And we wish, we are going to essentially work with this empirical process. So this was already presented in several talks and in Winfried's tutus one. So here we have, in this empirical process, two objects. We have, where is the red thing? No, yeah. We have the empirical distribution function computed from the available data, and we have a parametric estimate of F that's computed under the assumption that the null holds. That is, that there exists a theta 0 in the parameter space such that F is equal F theta 0. And in that case, if you replace the unknown parameter theta 0 by an estimate computed from the data, you get a parametric estimate of your distribution function. So the classical setting. So these papers, some of these papers have already been cited this morning. This is the so-called goodness of fit problem when parameters are estimated, and two prototypical statistics are the Kolmogorov-Smirnov statistic here and the Cranmer-von Mises statistic. And of course, you could consider minor variations of this in your applications. So the one important thing is that when you clearly want to compute p-values for when you base your goodness of fit test on such an empirical process. And in general, you have to keep in mind that the null weak limit of your goodness of fit process involves a drift term. Okay, I will briefly come back to that later. That drift term implies that your tests are not distribution dependent. So there are various solutions to that can be used. There is the approach of Durbin that Winfried Strutter mentioned this morning, also the approach of Khmaladze. While I can understand it in dimension 1, in dimension D, I do not understand that approach. My processor is too slow. So I need some other way to carry out my test, especially if I don't want to do what's done in this paper. So because I'm lazy and I have computer power at my disposal, I just think about the parametric bootstrap. So it's, as you all know, a generic, very simple way to carry out a goodness of fit of this type. You basically can implement it very quickly in R, for instance, as long as you know how to sample from your hypothesized model. You need to be able to estimate, but you need to do that to compute the test statistic, so that's okay. And you need also to be able to sample from your hypothesized family. In passing, I'm happy also to be able to cite, for instance, this paper, where the asymptotic validity of the bootstrap is investigated. And just a message also, showing the asymptotic validity of the parametric bootstrap is hard. It's not easy mathematically. For instance, the latest work I am aware is this one, and there the proofs are really complicated. So to fix ideas, just because I'm going to present an alternative to parametric bootstrap, I still need to tell you just to make sure that everybody has in mind what the parametric bootstrap is. So we are going to assume that the statistic of interest, the test statistic, is a continuous functional of the goodness of fit process. So we will write it phi of Fn, and you can think of Sn as the Kolmogorov-Smirnov statistic, for instance. And we are also going to assume that large values of Sn lead to the rejection of H0. So in some sense, Sn can be interpreted as a measure of departure from the null hypothesis that the unknown CDF belongs to the family. So the parametric bootstrap works as follows. You choose a large integer n, say 1,000, and you are going to estimate theta 0 using your estimator. So you will get f theta n as a parametric estimate of your distribution function. That will be a good one only if the null is true. Then you're going to repeat the following steps. For every k in 1n, you're going to generate a random sample from the estimated CDF. And you are going from that sample to re-estimate the empirical distribution function n theta 0. And you are going to form this replicate of the goodness of fit process. And so if you are under the null, and once you have your replicate, you just apply your phi and you get your replicate of your test statistic. If you are under the null, then intuitively you see that the larger n, the closer this is to the true CDF, the closer this is a sample from the true CDF, and the better, these differences in this case should be small, right? Okay, so you get every SNK for k in 1n, you can interpret it in that case and as an approximate realization of the test statistic under H0. And to compute a p-value, very naturally, you are going to compare your actual test statistic with these replicates. If your Sn is smaller than all or relatively smaller than many of these replicates, then you have no evidence against the null. On the other hand, if Sn is larger than most, you have evidence against the null. That's the parametric bootstrap. So this procedure, it's less and less true, of course, because the computing power is more available than before, but this can be very time-consuming because if you look at the previous procedure, you see that for every k here, you need to generate a random sample from the hypothesized model and to do estimation. And both steps can be very time-consuming if you have some complicated models. The idea here is just to draw your attention to a computationally more efficient approach that relies on a weighted bootstrap, or we've heard a lot about this weighted bootstrap. Some people call it a multiplier bootstrap, the wild bootstrap. There is also the Bayesian bootstrap. All these things are related. When you're interested in empirical processes, these are called these weighted bootstrap are related to multiplier central limit theorems, which are the key tools for proving the asymptotic validity of bootstrap procedures. Okay, and let me just give you an intuition. Let's say you have an IID sample with mean 0 and finite variance. Then consider another IID sample independent of the first. That's IID with mean 0 and variance 1. And by the multivariate central limit theorem, this random variable and this random variable converge jointly to independent copies of the same limit. And the limits are normal, but that's actually not that important for us. And another way of saying this is that conditionally on y1, yn, this thing converges to the same limiting distribution as this random variable for every sequence y1, yn. The idea of using this multiplier bootstrap, as far as we know, was first proposed in an article by Murray Burke, but he considered only the case of simple hypotheses. So this is not exactly what we need for the setting considered in this presentation. We want to have a method for estimated parameters that work with estimated parameters. Okay, so 8 or 9 years ago, Junian and myself, we gave conditions under which the multiplier type of test I will present are asymptotically valid under the null and the alternative. And in passing, we considered general empirical processes, so processes indexed by classes of functions. So to provide intuitions now, I will go back to the setting of multivariate distribution functions. So the setting is the following. We are going to assume that theta n is asymptotically linear with the influence function phi theta. So in this class, we have MLE, the MLE, we have minimum distance estimator, we have moment-based estimator, etc. And so this is going to be our central assumption. And then we are going to consider that, additionally to the data, we are given a sequence Z1, Zn of IID random variables with mean 0 and variance 1, satisfying this condition. And this condition is basically just the existence of a 2 plus epsilon moment. And we are going to consider this process, which we could call a multiplier goodness of fit process. And this process will be a replicate of our goodness of fit process. And if you think a little bit about the intuition I gave you earlier, this shouldn't surprise you. We are just basically using exactly the idea that's in here. Okay. So there are two parts in this goodness of fit process. There is a part that's related to the empirical distribution function, and there is another part related to the parametric estimation necessary to carry out the goodness of fit tests. This quantity here is the gradient of the parametric distribution function with respect to the parameter. Okay, so let me just give you some intuitions why this is supposed to work. So recall that the goodness of fit process has this form. Then, as already mentioned this morning, so then the corollary of our results is that under the null and suitable regularity conditions, these conditions concern essentially the behavior of the estimator theta n of theta 0. Then this goodness of fit process and the one that I just showed converge jointly in the space of bounded functions to independent copies of the same limit. So the intuition is as follows. This is your goodness of fit process, which you divide in two terms, as this morning. This converges to a Brownian bridge, and this will converge to the drift term, which I didn't give, but you can see it. So the gradient is a consequence of the delta method here. And on the other, so this is on one hand what's going on. On the other hand, you can decompose the multiplier goodness of fit process as follows. Okay, this first part here converges to a Brownian bridge, the same one as the first part of the other process. But if you look at things jointly, it converges to an independent copy of it. And this second part here you can basically show that it is under the right regularity conditions. It is asymptotically equivalent to this uniformly in X. And then this here, well, this is just a consequence of the central limit theorem, the fact that it converges to the drift term in distribution. Okay, this is the intuition. So this way I am presenting validity results related to consisting of showing joint convergence can be actually shown to be equivalent to more traditionally encountered settings. Restatement is the following. Under the null and regularity conditions, conditionally on the data, the multiplier goodness of fit process converges in the space of bounded function to the same weak limit as the initial goodness of fit process in probability. Okay, so you probably see where I'm going with this. So under the null, this multiplier goodness of fit process is close to being in an independent copy of the initial goodness of fit process. And every time you get a new set of multipliers, you get a new approximate independent copy. So very naturally, you are going to consider an additional, an alternative goodness of fit procedure. You can also show that things go well under the alternative. It's late, I'm not going to bother you. So the procedure is the following, which basically can be seen as a large sample alternative to the parametric bootstrap. You do the first two steps, which are exactly the same one that are needed in the parametric bootstrap. You estimate theta by theta n, and you compute your goodness of fit test statistic. And then you're going to do the following steps instead of the capital N steps in the parametric bootstrap. You're going to generate n IID multipliers, and you are going to form this empirical process and then a replicate of your test statistic. The interesting thing is that this part here, which is hard to compute, you need to compute it only once. And as soon as you generate new multipliers, you get a new replicate. So this typically, from point of view of the implementation, is just a matrix multiplication. And you compute your p-value in the same way as in the parametric bootstrap. I told you I would be quick. So some practical aspects and variation of this method. Let's just talk about, so the difficult part here is clearly the parametric part. And so this is faster than the parametric bootstrap, but there is a cost. And the cost is in this related to these functions, these influence functions. So for instance, in the case of the MLE, the influence function looks like this. So what do you have here? You have the probability density function associated with the parametric family. You have the gradient of that density with respect to theta, and you have the Fisher information matrix. So you need to have these quantities available or to estimate them. Note in passing that what we have is this and not this, of course. Okay. So a few ways to deal with the fact that for every model you need to compute. For every model you need to know these quantities. So to have a generic implementation, you of course need to be careful because everything will depend on your model. But you could consider you can compute gradients numerically, for instance, using Richardson extrapolation method. And as far as the Fisher information matrix, you can estimate it as a sample covariance matrix. Of course, when doing that, you need to add additional steps in your theory to show that these changes are asymptotically negligible. So in terms of finite sample performance, these tests should be regarded as large sample alternatives to the parametric bootstraps. We did implementations in many different settings, for univariate models, for multivariate models, for copula models. And basically, very roughly, what we observe is that the test we never found the test to be too liberal, which is important, and I agree with the comment that I'd rather use a conservative test than a liberal test. We also observed that the test for some models can be slightly conservative when the sample size is small. And very frequently, for when say this is very rough as a threshold, when n is equal to 300, we observe the powers of the parametric bootstrap and this multiplier procedure to be very close. So what are the main advantages and disadvantages of this approach? The main advantage is a computational. So if you have something that that requires a model that requires a large amount of computations, you're going to save a large amount of computation because you do only estimation once and you don't do random generation from the estimated model. And for instance, for some copulas, we observed a gain, a very important gain. The multiplier test takes minutes and the parametric bootstrap days. The interesting part is also that this test can be extended to time series. How would you extend the parametric bootstrap if you wanted to assess goodness of fit when you have data from a time series? That doesn't seem obvious to me. The main disadvantage is that these tests are harder to implement than the parametric bootstrap, which is very simple to program. Here you need some partial derivatives, but as I said, numerical solutions exist. Just another thing here. Another advantage is also theoretical, showing that this works is actually much easier than showing that the parametric bootstrap work, in my opinion. And some variations of this. So you find tests on you have this idea applied to general empirical processes, copulas. This is a nice paper where it's applied also to time series. Some people have used these ideas for dependently truncated data, characteristic functions, error distribution in non-parametric regressions. So it's related to the talk of Ingrid earlier. And I told you it wouldn't be too long, so it's over.
Do you have any questions for the speaker?
I have one remark. So at the outset, you said you make the condition of absolute continuity, but the parametric bootstrap also works for discrete distributions. Okay. So do you really need this?
I probably wrote that because I wanted to illustrate the parametric part with the MLE. So that's probably why I wrote that. But if you, for instance, if you consider in copulas, that's a bad example. But in some other settings, if you have a moment-based estimator, for instance, yes, and you don't need that, it's only related. This assumption was only related to the estimation of the theta. Yes. So
I really think it doesn't. It also works in other situations.
Right. This is just for illustration because I illustrated in this particular setting, and I wanted to talk about the MLE because everybody would think maybe first about the MLE.
Thank you.
So there are mainly two reasons to apply the bootstrap in an infinite problem. The first one is probably when you don't can estimate quantity, so you can get it by the bootstrap. And the other advantage is probably in some cases that you get what is called the second order correctness.
Right.
So you can estimate things which are more, say, approximate things better than using the asymptotic normal distribution. Do you have an idea if this multiplier bootstrap has this property?
So there is a nice paper from 1992 by Hausler and co-workers. It's where the weighted bootstrap is studied in the case of the sample mean, so not in an empirical process setting. And there they give the Edgeworth expansions for the multiplier bootstrap, which they call weighted bootstrap. And you have the same kind of second order correctness as for the Efron's bootstrap. So of course, I would very much like to be able to do Edgeworth expansions for empirical processes, but point-wise it's possible, but uniformly I don't know how to do that.
Any other questions? In that case, we can thank the speaker. Next talk is by Professor Wenceslao Gonzalez-Montega, and his talk will be on the goodness of fit test for the functional linear model with functional response.
Okay, thank you for the introduction. Well, first of all, I would like to give many thanks to Simon for the kind invitation representing the scientific committee, and also to Emmanuel for the help in the task of the organizing committee, because I think it's been a very, very nice workshop. It's the second time I taking part in this conference. Very good level, fantastic speakers. So then it's very nice in general. My congratulations for all. Well, I am the last speaker of today. I suppose that all people are completely killed or destroyed. But well, I will try to be more fast in the presentation. There are many slides, but I will try to skip and be concentrated only in important aspects of the presentation. Well, one interesting thing is we have in this project several people. Really, as you know, we have actually the experience of parallel computing. in this work, we have the experience of parallel research. So one of the guys is Eduardo García Portugués. Eduardo was my student. He was working in the thesis in directional data. He is very active, as you can see, in directional data. But in the additional time, being my student in the course of goodness of fit in the master, he also started the interest in the goodness of fit, our experience in goodness of fit to functional data. Well, Eduardo leaves Santiago. He's now in the Carlos III University. And by other side, after our last paper, at the beginning of this course, I received the visit of a postdoctoral person, Javier Liébana, who's coming from University of Granada for some days in Santiago, and say, well, maybe Javier would be nice to extend the goodness of fit for the functional response. And, well, he started. We were working along of 2 or 3 months. In December, I visited Carlos III, as always, with high frequency, and speaking with Eduardo, and say, well, Eduardo, I have to show you we got some advance in goodness of fit for functional model with functional response. And he told me, oh, but also me. And then we interchanged more or less essentially the same work. So then for that reason, he was... the work of Eduardo was as advisor of Gonzalo Álvarez Pérez, and then for that reason at the end I say, well, maybe we can put together our experience. Fortunately, I think we agree almost in all parts of the research. The research, essentially, from this part of the talk is quite computational, because I think in this moment we are more related with the computational aspects. We have in our almost finished paper, we have also some applications. I will not speak of applications of the first paper. And in the second paper, second part of the talk, I introduce additional now the applications to stochastic diffusion models. So this is also very recent, and I think can be a nice application of our first ideas for the models with functional covariates and functional response in the regression. So this is the reason of many people, because related with the last part of the research is Manuel Febrero, who is my colleague and very good expert in functional data. He has a very good packet in RCRAN. And my student, Alejandra López Pérez, who is interested in diffusion process, especially in the interest rate models. So this is more or less the history of different persons this time. Well, this is more or less the schedule of my presentation. As I told before, in our group in Santiago, there are people, many people interested in non-parametric aspects. Some people are interested in goodness of fit and other in functional data. And since 3-4 years ago, we started make interaction in the ideas of goodness of fit with functional data. So this is more or less the total with 1, 2, 3 points speaking about preliminary aspects and the introduction and new goodness of fit for the functional linear model with functional response. Also, in the case of functional data, it's very important the part corresponding to the estimation to the functional parameter. And additionally, there is a new line of research in these 4 points. This is a fruit of the work mainly of Eduardo and Gonzalo in Carlos III, with the idea to create a new hybrid approach for the estimation of the functional parameter. Well, there's also a package. I will speak a little bit. Maybe if I have time, I'll try to be fast because I know we have after additional double round and all the dinner or many things in a few time. I will speak a little bit of applications to diffusion process and some research lines. Well, we were working a lot for several years with different people and also receiving many of people of here have been in Santiago giving talks in the topic in goodness of fit, Holger, of course, Winfried, Ingrid, and many others. And in the last year, we started interested in to see the extension of this goodness of fit for the case of functional data. So, of course, there are many problems. We are, for example, in our group, we are very interested in the practical applications in environmental context, in energy context, and the high-frequency data produce a lot of functional data. As, for example, in this case, this is data of the Ontario data set related with the daily temperature and electricity consumption, and then we could be interested in to say there is some relation, there is some linear relation between these functional data. Well, so then, speaking of linearity, we can, of course, we can have the idea of linearity in the more classical case, this is multiply linear regression, and the more modern functional case where the sum is now changed by the inner product of a functional parameter with a functional covariate. Well, in the vectorial case, there are many tools related with the simplification test, as for example F-test, exploratory data analysis, residual diagnostic, or goodness of fit, not only for the linear, but for many models, as you can see in an invited paper I published with Rosa Crujeiras in test, where we make a big summary of the different goodness of fit for different regression models. Well, in the functional data context, starting with the simple case of scalar answer, we have the model, and maybe we can speak of different aspects. For example, the motivation is clear. We have many covariates observed in high frequency and can be considered in a functional context. With respect to the statistics are not for vectorial data, are for functional data. The atoms are functional data, and then the ill-posed problem is there present, as Winfrey gives some advices about these kind of problems in many other contexts. And also for mathematicians are very attractive because they like a lot different functional spaces, for example, semi-metric space, Banach space, Hilbert space. We will, in our more numerical work in this occasion, we will be more concentrated in the Hilbert space. So for the Hilbert space, again, we have working under the separability assumption. We have a countable base. It can be a fixed base, wavelets, B-splines, or base built with the data. Okay? And our idea, as in last previous 2 papers in this context, is to make projection. So translate our functional data to a finite approximation using mainly, in this case, the Fourier coefficients corresponding to the approximation of the functional data. Well, with respect to previous works in goodness of fit, because we can say when we can extend this philosophy, well, in the classical goodness of fit of the last 20 years, we have different papers. Here there are 3 examples. For example, one based on smooth ideas. This is a hot paper of Harlan and Mam in Annals of Statistics, 1993, using distance between non-parametric and parametric estimation in the, of course, finite-dimensional context. The paper of Winfrey-Stutig that was very commented in this conference, based in integrate-based test, avoiding the use of bandwidth parameter in many occasions, and also generalized likelihood ratio tests, extending the idea of the ratio, the likelihood ratio in the past, in the more classical context, in this case for the context where we have alternative non-parametrics. There are also many other papers. For example, Holger Detter has a lot of papers in goodness of fit in the 90s. Many of them related with, for example, with generalized likelihood ratio tests and many others. Also the tests based in the distribution of the residuals, as Ingrid commented in a previous talk. Well, we will be concentrating in the integrate-based tests. As I am telling here, we could see it already in many simulations studies that when we have a regression model that must be tested and the dimension increase, asymptotically, this kind of test has not influenced the dimension, but in the practice, yes. In the practice, there is a decreasing of the empirical power. So the idea was solved, in some sense, by Juan Carlos Escanciano. For me, it was very nice being the commission of his thesis, because if I am not wrong, this was material of the thesis of Juan Carlos and de Carlos III, where he said, well, to avoid the problem of dimensionality, we can use one projection of the process of Winfried using a projection of the covariates. So that means if I want to characterize the null distribution, I can characterize this using an alternative weight, not conditional to the covariate, but conditional to the different projections in all directions. Okay? So that means that I am building now one empirical regression process marked by the residuals and with indicator in the projections. And we to index U for the value corresponding to the projection and gamma corresponding for the direction. Juan Carlos got different results and published several papers related with this advance in this context. So this is exactly the idea that we get some years later in the context of functional data. Well, about the goodness of fit, functional model with scalar response and also for the estimation has many different papers in the maybe last 10 years. Cardot using functional principal component regression, the functional principal least square regression of Preda and Saporta, some advance that we could got recently using in the case in the missing and random data. And with respect to the goodness of fit, there are many advances, but relatively few papers compare, of course, with the big collection of papers in the more classical context. And one of the papers is with Eduardo, the first paper with Eduardo in these applications, where we are applying the approximations in all directions in the functional context. There are also some papers, for example, Del Sole et al. Using the ideas of Harlan and Mamen, some paper related with the generalized likelihood ratio test, and very recently in a paper published in Annals using random projections. But always, of course, for the context of a scalar response and functional covariate. For the case of a functional response, of course, the the estimation procedure is also more reduced. And in the test, we can find some papers that mainly concentrate in testing the significance of the functional covariate, not in goodness of fit. I know there is a paper, for example, of Kokosk et al. In some years ago, but making the test of significance inside of a linear model, not in an omnibus way. And also other paper of Valentin Patilea with some people also from my department, JASA, testing significance. They got also some advance for the compound hypothesis, but in the numerical aspect, he will be concentrated in testing significance of the covariates. There's a recent paper for a particular situation of functional data and concurrent models in Royal in 2018. But under our knowledge, apparently, there are not more research, of course, and my knowledge about the idea of make goodness of fit for the more general case. That was the reason I say to Javier Liébana when he came to Santiago and say, well, we can extend our ideas for the case of functional response. Well, in the functional response, we have this kind of model, okay? So the idea is we are thinking in the idea of testing the transformation from functional covariates to functional response using a linear operator, okay? This is the hypothesis that we are testing. Of course, mainly because apparently it's the model most used in the applications, as you can see in the book of Ranside and Silverman. And now then we have a linear transformation from one Hilbert space to another Hilbert space, where the linear operator can be rewritten, of course, as an infinite sum with respect to the tensor products of the different elements of the base for one space and for other space, functional and answer. Okay, and then the idea is to extend, of course, the null hypothesis of this model, okay, in a general way. Of course, then the idea is make now projections in the direction corresponding to the functional covariate and also to the functional response, and create the empirical process indexed, of course, in the corresponding scalar value U, and the directions of projections corresponding to the answer and to the covariance. Well, I think a very nice open problem from theoretical viewpoint is, of course, study the behavior of the empirical process of this test. It's not our knowledge not known. Okay, and the idea then say, well, we have more or less the C of the architecture of different tests, and we can define different transformations. One transformation is the Kramer-von Mises based on the L2 transformation. So this is the L2 transformation, and the idea, of course, to forego to the practical aspects, is make truncation in the corresponding covariates with P elements of the base, Q elements of the answer, and try to rewrite this functional in a very kindly way for the computation aspects. Well, this is, of course, this part we use a lot, the ideas of Scanciano, because in some sense we were working with the finite dimensional aspects, in this case corresponding to the Fourier coefficients of the different elements of the functional covariates and the functional response. So after an exercise of algebra, it's possible to write the test in this practical way, where here this matrix is known because it depends of angulus, also calculate in previous papers, also calculate in the for first time in the paper of Juan Carlos Scanciano for the case of Victoria. And the other one, it had correspond to the residuals in the Fourier coefficients under the truncation of our problem. So in fact, this practical aspect allows to create a machine of, in this case, of Bootstrap to make good calibration of the test. Well, so the idea is, of course, first the estimation of beta, by the moment I will not speak, we can make one estimation of beta and then create residuals and then compute the statistics, draw IID variables of mean 0, variance 1, while bootstrap style, and then create our vectorial bootstrap residuals, multiplying the original one by this error, mean 0 and variance 1, re-estimate the beta parameter, get the bootstrap residuals, and then calculate the computing statistics and repeat a lot of times. Okay. Well, essentially, if we are making a discretization of our functional covariate, functional answer, and also the operator, the functional linear model with functional response, in some sense, can be written as a vectorial general linear model in terms of the Fourier coefficients of the covariates and on the answers. So this is more or less the developed expression in matrix language with the corresponding error. And of course, the question is, well, to make practice the procedure, we have to estimate the B parameter. And for the estimation of B parameter, what we have in the literature? Well, of course, one possibility is use the least squares of Ramsey and Silverman in 2005. But of course, we have a problem here, which kind of levels P and Q use, and how we can make the estimation of beta, because in the case of functional data, we can find, of course, the context of sparsity and many other problems. So then here start the idea develop for the estimation based in design some kind of cutoff levels for Q and P, then use in a second step a lasso estimation to select variates, and then with the selected variates, in this case variates are the Fourier coefficients, that we can have problems that be close to 0 and create the ill problem, of course, and try then to use one least square estimator. The advance of this point is that we can write our prediction, our estimation with a hat matrix, and don't lose the advantage that we had or to explain very well our statistics tests. I have many simulations as the time is going very fast. Well, with respect to the estimation of beta, this hybrid estimator we call FPCR L1S that use in a first step lasso and then the least squares, in general outperform under different scenarios. I will not go into the detail of the scenarios because in other case I cannot speak anymore. Okay. With respect to the test, was very useful the package that was commented yesterday. I don't remember, maybe by Juan Carlos, of Eduardo and Javier, because with the help of package, it was possible to make a very intensive simulation study that we developed in the power center station of our university, because really require a lot of time in the simulations. In the package I think it's not still sent to Eduardo. Maybe you want to say something about that. It's in progress, but it's almost finished, no? Okay. And then they have a lot of facilities. And with respect to the different studies we made the goodness of fit for the case of single null hypothesis. This, of course, is including the case of significance of the covariates. We made the comparison under different scenarios, different beta parameters, different alternatives, different sample size, different explained variance, different cutoffs, many different possibilities in this simulation study. Many numbers, of course. The summary is our approach is well calibrated. The procedure of Kokoschka is working well in the case on the functional linear model, of course, because it was designed not for general alternative, but is designed in the context that we have a linear model. we have a competitive behavior with respect to the test of Valentin, but of course I will not go in detail with these numbers because there are many, of course. And with respect to the compound hypothesis, again, many different scenarios. In this case, no competitors. Okay? We use our procedure, okay? And also we could see a good calibration and a good power in the behavior of our tests. Have 2 minutes? 3? Well, a nice thing we have in our first part of the talk, first paper, we have also nice applications, but I prefer show you not application with real data, but one application for a field. Because in the case of diffusion models, typically we will have stochastic differential equations. This student, I have Alejandra, is a very good one, but from economical world. And she's very interested in applications to this context, more related with economy. And well, so the idea is to design goodness of it for this kind of stochastic differential equations. So very fast, for example, we can have CKLS model that included the case of Ornstein-Uhlenbeck process and many others in the literature, in this case, without stochastic volatility. Okay? Well, some properties, I will not go into detail. And the idea is to go back to the previous works of Dennis Box. In fact, the iteration with Javier was because he arrived to Santiago after being with Dennis Box for some months working in the time series of functional data, in particular in the autoregressive Hilbertian spaces. So if we have in interest rate models, for example, or other interest economic process, we can cut our data in different windows and create functional covariates and functional response. So the idea is say, well, can apply previous methodology to this general context. Well, for example, in the case of the Ornstein-Uhlenbeck, the functional response can be rewriting in an integrate way in a language of autoregressive Hilbertian process. So this is also possible in a general autoregressive, not only autoregressive of order 1, but with autoregressive of order P, I can rewrite the process in a language of functional linear models with covariates and answer. Okay? So using this idea, so we say, well, we can design this kind of test. First, we rewrite our process in this language. We test, firstly, if we have a linearity using the previous test in the first part of the talk. If we reject, of course, the process is completely rejected because that must satisfy the relation. If we accept, then we are in the functional linear model with functional response, and then we have to try it if we have certain parametric expressions corresponding, for example, to the Ornstein-Uhlenbeck process. So then maybe we F-test or any other with Bootstrap parametric calibration. And the comparison, I already got one paper using philosophy of Stutte. There are papers of smoothing contest, mainly based in that discretization of the differential equation. And in general, this new procedure worked well in the calibration. And we are now starting to see what about the power, well, with physics alternatives is clearly working well, but this is still a point that we have to be careful with the contiguous and many others. This is, of course, a very, very, very starting points. There are also applications, but I think there are some research lines for the future. All the people, I think, is tired. I also me. So thank you very much for.
There's about 2 minutes for questions.
Yes, Valentin.
Any questions?
Yes, Valentin. Yes.
Thank you for the talk. It was very interesting. So just a comment, as a lot of people in the in the room now, there are two schools for testing. Well, the ones based on the work of Professor Stute, of course, and the others using smoothing techniques. And when you start from the smoothing techniques, basically you look at an object that I used in my talk, the norm of the conditional expectation. I say the norm because now you are in a multidimensional framework for the response. So it's no longer the square, as in Fan and Lee, it's the norm. Well, I would say that in this setup, the smoothing approach has an advantage, as when you write the U statistic, you keep the norm of the residuals. So there is no need for doing projections on the response, on the residuals in this type of test. So I would say it's 1-0 for smoothing versus marked empirical for this particular setup, because you have one less problem to solve, to the index gamma on the error term.
Well, I have not a special position with respect to one or other school. I work, Winfrey can speak a lot.
What's the reply?
Well, but only maybe Winfrey prefer reply. I don't know, but only one comment is in the case of the smoothing contest, the problem is the parameter is also functional, and then you have to forgetting in the compound hypothesis, you have to again also with the rate where you're estimating the beta parameter. In this case, is functional.
I think they are the same type of problem.
Well, but this is not root n, for example. No. In the case, in the finite dimensional case, is root n estimation, so have not influence with the smoothing in the limit distribution. Here,
we'll talk about that.
Okay.
Thank you.
So U beta is a kernel.
Yeah.
Depending on
In
S and K, it's a kernel.
Yes.
So that is something which was introduced to calculus about 100 years ago. And in calculus, it is called the Trento operator. Yeah? So, and these people in calculus, they studied very carefully the possibility to invert this operator. So let me start with a negative thing. The inverse operator does not exist. So that is very, very bad. Yeah. So from multivariate statistics, you know this least squares business. This appears also in the infinite dimensional case. But these operators can be computed, and all this together result in a so-called singular value decomposition. So this inverse operator, yeah, is not inverse in a naive sense, but it is exactly what is called the Moore-Penrose inverse operator. Yeah, that exactly is the least squares business. Yeah, so the least squares business, what you know from the finite dimension, is that an inverse operator? So yes and no. Yes and no. Yeah, and this has been extended to the functional case by these people in calculus. So there are very nice kernels, the beta, which are symmetric and non-negative definite. So and these are the covariance kernels. So if beta is a covariance kernel, then you can decompose this kernel in terms of a series. And that is called Mercer's theorem. So Mercer's theorem is very, very important, for example, for Cahun law F. Yeah? So, and also this eigenvalue theory for this kind of kernel is very nice because all the eigenvalues are non-negative. And so you can order them. And that is more or less what we do in principal component analysis. So all this stuff has a background which goes back more than 100 years in calculus. Okay? So what I don't know, I have not seen any assumptions on beta. Like so the operator is non-negative definite. So I have not seen anything in your talk.
Yeah, no, but
So therefore, for betas which do not satisfy this Mercer business and all this, I don't know. So there are low pass filters, but I only know that is all possible for this singular value business. But I don't know what you can do. And so cutting the series means a projection. So you can do this, and now you answer. So it's not a 1-0, it is a 1-1.
Okay, thank you.
Oh yeah, let's go into detail. You see.
Okay.
Okay. I think we're out of time, so we can thank all the speakers of the session.
Thank you.